some cool spring sports. Anyone going to the basketball game tonight? I'm actually going, and so we'll probably lose. No, I'm saying we're probably going to lose because I haven't been able to go to another game, and now I'm finally going. Whenever I can finally go to things, we tend to lose. I probably should just not. All right, so last class we did some review, but the class before we were talking about the fundamental theorem of calculus. Just to review, we did that a couple of different ways. The first way was, I'm scrolling way too far. When we were actually able to integrate our function, so we were able to find an antiderivative. So like in this first example, when we could take x cubed and go to 1/4 x to the 4th. And that fundamental theorem of calculus was when we plugged in the top bound and subtracted when we plugged in the bottom bound. We got a little bit more interesting by connecting back to area. So we're finding the area bound between the curve and the x-axis. We did a couple of interesting questions where we got to interact with a question that had a constant in it, a question that had a table, and then we peered at this graph guy. Just to give a quick overview, because we're going to do one like this. It had two different questions in it, but to do the G of 3, what we did was we found a bound that we wanted to know about, which is that x equals 3, and the bound that we did know about, which was that G of 0, so that x equals 0, and those were the bounds on our integral. We did an integral because we had the graph of G prime, but we were asked about the graph of G. So to remove that prime, remove that derivative, we did an antiderivative. We were able to use our idea of connecting back to area to evaluate the integral, and we put stuff on the other side. Hello, Quinn. We put stuff on the other side that we were given. So we're going to do the same thing with this graph. If this graph looks familiar, it's because I use it on pretty much every set of notes, quiz, and test ever. It's in the problem set. Just a really great graph, and I think it's a recent graph. I think it's from like 2018 or 19, which is why I keep using it. Notice in the question, they are confirming some things for us. They're confirming that that is indeed a semicircle. All of those things are indeed line segments. What is the most important piece of information they're giving us in this like top paragraph thing? Yeah, the one point that we know on the graph of f, because this is the graph of f prime. So if I'm looking at finding something like f of -6, my answer is most certainly not going to be 2 because that is f prime of -6. So let's go ahead and we're going to set up our fundamental theorem of calculus like we did up here. So I know that if I integrate f prime of x, I will get f of x. I need to choose two bounds. My goal is for the first one is going to be to find this guy, and then I'm going to let you guys find f of 5 probably. So what two bounds do you think we are going to use for this question? -2 and -6. -2 is a good choice because I'm given that information in the big top paragraph. F of -6, so that -6 is a good choice because that's what I'm trying to find. Which one are you guys going to put on top and on bottom? -2 is on top, -6 is on the bottom. We want to go kind of numerically. So think of on a number line, -6 would be on the left, -2 would be on the right. So you're just switching that from bottom to top. We're going to do that one second. So it's kind of like these are two separate problems, but we will use 5 in our next question. All right. As we remember, this is us plugging in our bound. So we would be doing f of -2 minus f of -6 to be able to plug in. Now, this integral, I don't know what function f prime of x is. So what do I know about integrals if I'm working with a graph? It means area. And in this case, I mean the area from -6 up to -2. When I'm drawing on my picture, a lot of you were asking really good questions last time of like, what can I draw on my picture? Any vertical lines to kind of cut off your bounds are fine. You can also draw along the x-axis. So what shape am I finding the area of? Yeah, this triangle right here. Do I need calculus to find the area of a triangle? Whoa, Herbie's just telling me knowledge. All right, 1/2 base times height is the area formula for a triangle. Do you guys agree with his 4 and his 2? Perfect. All right, 4 along this base, 2 along that height. You can confirm that too from the y value of that point. All right. Is there anything else I can plug in that I haven't plugged in yet? Yep, I can make the f of negative 2, 3. So this is going to be 4 equals 3 minus f of negative 6. I'm going to do kind of 2 things at once. I'm going to add the f of negative 6 over and subtract the 4. And then divided by negative 1. That's cool too. Algebra. You can do it lots of ways. So I think any way you solve this for f of negative 6, you should be getting negative 1. Because we were looking at the bounds negative 2 and negative 6. So I want to go, here is negative 2 right here, 3, 4, 5, negative 6. So I only want to work between those two x values. Why do you not like that answer?
I thought so. You did not do it.
So if you subtract the 3 from both sides, you get 1 equals negative f of negative 6. Divide by negative 1. Or you can, I added this guy and then subtracted the 4 personally. That's a great question. So the problem with looking at just the area of the graph is we now have this side that we're interacting with. The thing that's actually happening is we have this positive value 3, and we're actually adding the area, but it's going backwards to get to negative 6. So it's almost like we're starting with the value 3, and then we're subtracting the area of that triangle because we're kind of counting it backwards if we were at the starting point and just going with the area. So that's how we plug in our bounds for fundamental. We have to plug in the top bound first. All right. Shall we do the next one together just to practice? There's lots of questions, so I don't want you to feel overwhelmed. Do you guys want to try the next one on your own or together? Yeah. Together. All right. If you're feeling gutsy, feel free to try to race us through it because I'm going to be explaining it. So if you want to try it on your own, definitely you can. If we're working with f of 5, again, we want to do an integral because we're looking to go from f prime to regular f. To get rid of a prime, we want to get rid of our derivative. Let's do an antiderivative. Do you need one of the desks that doesn't have a thing underneath it? Okay, I'm going to say Mallory's got a lot of leg room.
Yeah, you don't need all that leg room.
As someone who also is tall and interesting. All right. So I'm going to eventually be doing f prime in my integral. I'm going to get f, but I need 2 bounds. Does anyone think they know? All right. So looking at what we've got, we want one that we know about. I'm going to switch colors. Perfect. We want also the one that we're trying to find. Herbie's right that I could use the f of negative 6 that I found in the last question. But like you said, since negative 2 is closer to 5, there's less area that I'll have to find there. So it's a little bit easier to use negative 2 up to 5. Now, do you guys like the direction that I wrote them there? Negative 2 on the bottom, 5 on the top? Yeah, we want to go from lowest to highest. Both kind of numerically and directionally. So that's going to do negative 2 here and 5 here. I'm going to use the fundamental theorem of calculus to plug in these bounds. Which one goes in the first set of parentheses? What? 5. It has to be that top bound based on the fundamental theorem of calculus, negative 2 here. All right. Again, we don't have an integral to, we don't have a function to integrate to evaluate this integral. So we have to use the graph. What does an integral mean on a graph? Area. All right, let's find our area. We're going from negative 2 up until 1, 2, 3, 4, 5. What shapes do you see? Cool, cool, cool. What? Negative. Oh, okay. Spoiler alert. All right. Anything you guys want to tell me about this semicircle?
Yeah, that is half the area.
Okay. Cool. So we have pi r squared divided by 2. Anyone else want to tell me about this semicircle? There's something calculus about it that we need to remember. All right. My semicircle is below the x-axis, so I have to count its area as negative. Now, man gave us that formula for it. What is the radius of this semicircle? 2. You can go to its center and count out 2. All right. Is that the only shape, or do we need more shapes? The triangle. How do I do triangles again? Is it 4? I only count 3.
Oh, yeah.
All right, 3 times 2. Cool. For some reason, a lot of my BC students wanted to break the triangle into 2 triangles. I don't know why. I think they were just being extra, but you can if you want, if that makes you happier just to have right triangles. All right, f of 5 is what I would like to find this time. And then anyone remember what f of negative 2 was? 3, that's given in the question. If you ever think you need more information, look at the paragraph. It's usually there. All right. So I'm going to simplify a little bit, but theoretically, you could just add the 3 over and not really simplify at all on the free response portion of the AP test. I'm going to do it just for fun. So that's 4 pi divided by 2. That's negative 2 pi here. That's plus 3. Oh. Looks like Herbie was wrong. Perfect.
I changed the answer. You didn't hear it.
Okay. Thank you. So I'm going to add 3 to the other side. So I'm going to get negative 2 pi and plus 6. Again, we can't really confirm this anyway visually because we don't have the graph of f, but we are getting an answer using our area for our integral and our given value here. These are pretty popular on the free response. I can guarantee you there's going to be one on the Unit 6 test. All right. So I'm going to hand out some notes in a second, but we're actually not going to take notes. We're going to look at the back page. You're going to notice it says, what do you notice on it? So it's going to be something called, oh, please don't die. Sorry, my computer has been getting feisty. So I'm going to give these to you in a second. I have not taught you how to do this yet. So there are no wrong answers yet. I just want you to be brave. This second fundamental theorem of calculus talks about what happens if I take a derivative of an integral. I want you to try to figure out what's going on. So I'm going to give you a few minutes to just talk to your table, come up with any ideas. We're going to share those ideas out and see if we can figure out what it is. This is something I won't really be able to prove rigorously to you, but I'll be able to kind of show you an example of why it works. It's a little bit weird, so we'll practice it, and then we'll see how we use that on the AP exam, and one cool conclusion called average value. So I'm going to pass these out kind of upside down so you have this here. I want you to look at it. There's a couple of different examples. We're trying to figure out what happens when I take the derivative of an integral.
So should we try and solve or just write what we need?
No, so these are like already done. So it's like the problem's already done. I want you to figure out how did I do the problem? Where is all the stuff coming from? Try to have at least a couple ideas of what you could share out in any of the problems. I'm just going to give you like 2 minutes to think about it. Oh. That's why. How do you have your chemistry book out? Don't multitask my class. That's rude. I don't multitask you guys.
Wow.
1, 2, 3, 4, 5. Then 1 C times. I also asked you to do something very specific. It is true that I could have multiplied by 1 here. All right. Anyone want to tell me anything they noticed about this? Anything mathematical? If you won't share, I will make you share. Yes, Onyx, what do you notice?
Top down, and then it's multiplied by the derivative.
Ooh, okay, lots of noticing. So top bound somehow gets plugged in. All right, top bound plugged in net, you're adding to T. And then something about a derivative. Okay, so multiply by derivative. All right, did anyone notice anything else or want to put some different language on it? Or why does problem number 1 not get multiplied by anything? Yeah.
Wait. Isn't that not case though?
For which one?
For number 1.
Yeah, where is this one? Doesn't look like it's getting multiplied by a derivative. By 1. So what am I multiplying by the derivative of?
All
right.
Where's the chain rule? Where's the
Ooh. All right.
this was the chain rule?
Yeah, so this looks like it's kind of a comparison to chain rule. So kind of chain rule. But Matt's right that it doesn't look like we're chaining like what we would normally consider the inside function. What are we considering the inside function here? Yeah, that top bound seems to be working as the inside function. So we have a little bit of a difference between what we would normally consider our inside function because of this situation right here. Anything else we notice that maybe doesn't affect the problem at all? Yeah, does anyone notice anything happening with the bottom bound? Are they all something similar? All right, they're all bottom bounds, all numbers.
If they were a variable, it would be
Yes. We won't really encounter that. That'd be more of a BC style problem. I can touch on how you would deal with it, but we won't see anything like that. What else? What else? What else? Anyone notice anything kind of about this part? That's a very vague question. Yeah, so what do you guys think would happen if I do the derivative of an integral or the derivative of an antiderivative? Yeah, you would expect relatively nothing to happen, right? You would expect them to kind of cancel each other out with maybe a little bit of a consequence. And this is the consequence that's going to happen. So we're going to talk about this today, and we're going to talk about it in our notes. So if you want to flip back over to the front, I'm going to put some formal language on this. We'll take a break after we practice these kind of super explicitly, and then we'll come back and talk about how this is actually going to get asked about on the AP exam. So this is actually called the second fundamental theorem of calculus. Some textbooks have it being called just the fundamental theorem of calculus. It's a conclusion from the regular one. So what's going to happen, I'm going to write this kind of a really explicit way. It's going to be a little obnoxious, is we're taking a derivative of an integral. For us in AB Calc, the bottom bound is going to be some number. So I'm just going to call it A. And the top bound is either going to be X or some function G of X. You're going to have a function in here. Was anyone creeped out by the T at all? All right. The T is kind of just a holder variable. Since we have that X up in the top bound, it could be any letter you want as long as it's not a letter that means something else. So it could be M for Matt, H for Herbie, not E for Emery because E means something else.
Yeah.
Yep. That's fair. He could use an uppercase E. All right, so what's going to happen here is we kind of expect to get out f of x. We kind of expect the derivative and the antiderivative to cancel each other out. The problem is we have a top bound that is not just x. So we're going to plug in f of g of x, but now we've created an inside function. So we're going to multiply by the derivative of that top bound. Now, most of the time when we do these questions, especially when they're embedded in a free response question, is we're going to be using ones that have a top bound of 1. That's generally the ones that you're going to see. But there are some options for multiple choice or some other crafty questions where that top bound will be something. Man, absolutely. All right, so the main idea is that these are inverse operations. Yeah, with some chain rule. If you're, do I need to move stuff? All right, cool. So it's kind of like if you've ever talked about the square root of x squared, that you feel like that you want it to be x, but it's actually not. It's actually the absolute value of x because of some sign changes. So sometimes our inverse operations don't do exactly what we want them to do. So that's kind of the chain rule piece here. So we're going to practice this a couple of times, and then I'm going to show you one. I put proof in quotation marks. I'm going to brute force this one by actually taking the integral, then taking the antiderivative. The point of this is that we shouldn't have to brute force that, but I'm just going to show you how it would work to do that. So here we're taking the derivative of an integral. So we're going to essentially write the regular function with the top bound plugged in. Like Matt said, to where t is. So I've got x squared plus 1. Do I need to chain rule in this one? No. Top bound is x. You could write times 1 for the derivative of that top bound, but yep, that's the whole answer. All right. So it's the derivative of the integral. So that's why it looks so similar to the normal one, is we're doing a derivative of an antiderivative. So it's almost like we went up a layer and then took a layer off. All right, here, what would you guys expect this one to look like? Cosine of x cubed, and I heard times, sorry, I cut you off, times 3x squared. So again, we're taking the derivative of the top bound. Now, I'm going to take this second one, and I'm going to show you what would happen if I actually did integrate this and take the integrate this, then take the derivative. Because I think it's interesting to see why the bottom bound doesn't matter, why the chain rule is there. This process, though, is one that we normally can't do. Normally, we're not going to be able, like this guy, you guys will not have the skills to integrate that this year. I actually don't think I currently have the skills because I think you have to use trig sub. Is that right? Do I need trig sub for the square root of t squared plus 1? I can't think of a way to do that. You'd probably have to use like trig, because trig makes everything better. So I'm going to do this one while Quinn figures out how to integrate that probably. Up here, again, this is probably not something you would do, but I just want you to see kind of where the pieces are going. If you want to, or you can just watch, either one's fine. All right, does anyone remember the integral of cosine? What function has a derivative of cosine? Let's try that again. Sine of t. All right, here my bounds were pi over 2 and x cubed. So now I'm going to plug in my bounds. I'm just keeping the derivative because I haven't done that yet. Which of my two bounds will go in first? The x cubed will go in first. So I'll have sine of x cubed minus sine of pi over 2. All right, so I did the antiderivative. I plugged in my bounds. Let's now take a derivative. So taking a derivative of this guy, does everyone see that that's now going to need our chain rule? So we're going to have the derivative of sine is cosine. So notice we went from our antiderivative, we went to sine, but then we took a derivative straight back to cosine. That's why we're getting the same outside function again. But when I plugged in that bound, it now created that inside function that I need to chain rule. Can anyone see why this guy is not going to make any difference to the problem whatsoever? There's no x, so the derivative of that is 0. It's a number. So as long as that bottom bound is a number, if I took an antiderivative, plugged in my bounds, and then took the derivative, that's going to go away. So the problem with that is really what you would want to do for rigorous, like actually using this theorem, is you would probably want to split your bounds. So you'd split somewhere in the middle, and you do an integral from the bottom bound to maybe 0, and then from 0 to the top bound, flip some stuff around. It's a complicated process, which is why I'm saying it would probably be a BC question. I've never seen one with multiple variable bounds either way. All right, so let's just practice. What I want you to do is this way. So not the like brute force it and go back. I want you to just practice using this guy right here. So for example, the first one, we're taking a derivative of an integral. So we're finding f prime. That's the derivative of this. We plug in our x where t is. If we need to, we multiply it by the derivative of that top bound. So take a second and try the other three. You can leave them very unsimplified. Mm-hmm. What? This guy? That's the name of the function, and we're finding f prime. Because that's what they named him. Yeah. Okay. How gross. Ooh, arc? Oh, hyperbolic. Oh, that's real gross. Either. Yeah. That's interesting that the front end looks nice, though. That looks like you would integrate by parts. What even hyperbolic sign? Isn't that like? I don't remember what it is. I've seen it. It's in the Larson books at the front end. Is everyone already done? No? You're done? All right. If I can get some people to tell me some answers, we can take a break right now. You can do the second one? What do you think? What? I think it's just this guy. Are we doing the same question?
Oh, yeah, my bad.
Were you doing the bottom one?
No.
Oh.
I just forgot the bottom.
Oh, gotcha. All right.
Times.
You actually don't need to times anything because our top bound was just x. So if you times anything, you'd just be multiplying by 1. All right. Anyone feeling this guy right here? All right. I'm starting with -2. Instead of t, what will I write? X squared. Will the +2 come along for the ride? Yep. All right. Times 2x. That's coming from the derivative of our top bound. Using parentheses to make sure I'm multiplying by everything. All right. Did everyone have fun doing the last one? You got this one. You're going to list the whole thing out? All right. I'm ready.
negative 3x cubed.
Like this?
Yeah.
Definitely. Okay.
Plus 11 squared minus 39 plus 44 times, and then times all of it by.
Cool. So, as you can imagine, this is not the most interesting process just in and of itself like this. So we're going to preview the question we're going to do when we get back from break, and then we're going to do them when we get back. Most of the time what happens here is we're going to be looking at our accumulation functions. We saw those a couple of classes ago, but notice now they're starting to ask me about things like H prime and H double prime in here. Same thing with this question at the bottom, very similar looking graph. We've got an accumulation function, but now they're starting to ask me about the derivative of that accumulation function. But notice in this case, both of those top bounds are just X, so it's not super complicated. All right, let's take 4, and then we'll be back for some more calculus. Oh, yeah, you could definitely. Oh, you want to be careful, like this one right here. You'd want to square the 3 first, so that would be 9 times your 11 to make sure you're not doing 33x squared, because you got to do your x in PEMDAS, you got to do your exponents first. Yes. Queen. Mm-hmm.
Cosine H.
Is that on the complex plane?
No.
No, I thought it had like e's in it.
Oh, it does.
It does?
That's why
Okay.
you do, like, you actually draw it, but currently it defines unit hyperbola.
Like unit hyperbola?
Yeah.
Yeah, because doesn't it has e's in it, right? Why does it have e's in it though?
That's like the way it's defined. I was just looking at it, they define all of it.
No, I need to learn new things. It's been a while since I learned anything. Because there is, I remember them being in the Larson book. Because the Larson book has this cute inside cover. I was like, oh, yeah. Actually, this was my calculus book from high school. The way you guys took over. Oh wait, no, maybe it was a different one. The way you guys took over for. But it has this cute inside. Yeah, it has the hyperbola.
Yeah, it is. You're supposed to say them. Your person
It's just like.
This was in high school. This was me as your
Still not
in college. 16 problems on finding limits numerically in traffic. You know, expectations have changed. Yeah. I've also. Yes. I think we weren't doing. We did all the same things.
So if you're deciding which x is equal to either x minus b or x all the time.
I actually had that right in my head. Why do I know that?
So it was important at some point.
I think I just looked it up at some point. I was like, what is this? And then I was like, ease? I think that's why I thought I had to do the complex thing, something like e to the I pi, you know? I don't know. Oh, my timer's done. I got so distracted. It just ended. All right, let's get fun and festive with how we're actually going to use this on a question, on a quiz, test, AP test, stuff like that. I find these utterly thrilling, which means you're definitely going to see one in the future. Particularly, I love this multiple choice question, very AP in style, that we're going to only have certain amounts of information. So let's look at, everyone notice the answer choices are very much about the X value 6. All right. So I'm going to try to write as much as I can down about H of 6, H prime of 6, and H double prime of 6. So let's start with H of 6. That's just me plugging in 6 to that top bound. What does, we don't have a function or anything. So what does an integral mean on our graph? Area, right? So we're looking at area from 0 all the way over to 6. What do you know about that? It is a weird shape, but can't get like an exact number. Okay, I could try to approximate. I want to go a little easier. Y'all, if you've got your phones out, just like leave. I don't need to beg for your attention. Come on. There's only a few of us. Let's get rolling. What do you know about this yellow thing? Why do you know it's negative? Below the x-axis. I could put an estimate on it, but I at least know that this is negative. All right, let's say I take a derivative. Taking a derivative of this integral, what is going to pop out of that? We just did this before our break. All right, I'm going to take the x. I'm going to plug it in. So I'm going to get f of x. Will I need to, not f of x in this case, will I need to do any chain rule at all? No. So this is going to look like f of 6 because h prime of x is going to be f of x. We're plugging in that top bound. All right, what do you know about f of 6? It's 0. On this graph, that is the y value, so it is 0. Notice we're trying to put these in order. So can you put two things in order that one is 0 and one is less than 0? Yeah. Oh my goodness. Cool. So what Herbie's noticing, if I take another derivative, it's kind of like I'm doing the same thing to both sides. Back in Algebra 1, you could add to both sides, subtract to both sides, multiply to both sides. Here, we're just taking a derivative of both sides. What does a derivative mean on a graph? Slope, right? Looking at right here, what can you tell me about that slope? Positive. So while I have like no information about this function other than this graph, I am able to order h, h prime, h double prime. It's not even a graph of that function, and I already have enough information to answer this question. Let's see if your eyeballs are good enough. What is the answer to this question? All right, we want h, then h prime, then h double prime. That sounds good to me. The first one. Yeah, we said less than 0 because all of that area is below the x-axis. We could have done even farther. So like I would be pretty convinced even if they asked like h of 9, that would still be negative because the yellow part is bigger than the other part. But they're going to get us pretty convincing. All right, the next one. Again, very similar looking graph. These graphs all look the same. That front top paragraph gives us important information. It confirms that those shapes are what we think they are, the semicircle. They even tell us where it's centered. But notice this time we have an accumulation function. So this is unlike the questions we did at the end of the 6.4 notes where we were looking at kind of a function's derivative and being asked about the function. Here, we're trying to find values of this function. So let's do g of -2. I'm going to set you up, and then you guys are going to find it for me. So plugging this guy in. I've got 1 on the bottom. What number is going on the top? -2. Ew. Anyone else creeped out? What? that's where x was. But is anyone not loving that negative 2's at the top? Yeah. How could we switch it to the bottom? Yep. So we can add a negative sign so that we can find area in the correct direction. So what I would like you guys to do, you're going to slap a negative sign out front. I want you to find me the integral from -2 to 1. Try to simplify it as much as you can if you would like to. So you're trying to evaluate that integral based on the graph. I asked you now what an integral means on a graph multiple times today, so hopefully you know. It's a word, 4 letters. I just want to make sure that anything below the x-axis is counted as negative. You guys got an answer yet? No, just leave it in terms of pi. Nobody applying your answer. You could do decimals if you want. I'm usually team fractions. We've had this fight before. Derek.
I think Derek's had this fight.
All right. Is it that thing and this thing? Did I do my shapes right? Ooh. Thanks, Evan. Thanks, Matt. All right. So for this guy, let's see, that triangle is 1/2, 1 times, how tall is he? 3. I love when they label the points. All right. And then the semicircle is pi over 2r squared, or pi r squared all over 2. What'd you guys get for the radius of that guy? 1. All right. What should go here? Minus. Why? Below the x-axis. I put mine over the under the pi, but you can put it all the way under if you want. What's up? Nope, that would be the diameter. So you're centered here, and you're only stepping out 1 to that x value. All right. If I simplify this, I would probably write it pi over 2 minus 3/2, distributing that negative in, but you could just leave it whatever you want. All right. Task number 1 complete. Task number 2, we want to find g prime of -3. Let's start by finding g prime of x. Looking at that function, we've now done it a few times. What is g prime of x going to be? So we're taking a derivative of this integral. What is g prime of x? Thank you. F of x. So if we're looking at g prime of -3, that's f of -3. What? Because we're taking the derivative of that integral. The thing we've been doing today. Those are effectively going to cancel. We're plugging in our top bound, chain rolling it if necessary. F of -3. What does that mean on the graph? Like, what are we looking for? Are we looking for area? Ooh, a point. All right. So -3. -1, 2, 3. Are you sure? All right. You can tell by the slope. So we want to be sure. Looking at this, it looks like it goes up 2 over 2, which is the same thing as up 1 over 1. It's nice to confirm that in your head. You don't want to assume anything off the graph, but I do agree with you guys. It is 2 in this case. All right, so that was coming from our y value. All right, last one, we're looking at g double prime. All right, let's look. Do you guys agree with Herbie? If we take one derivative, We're not doing slope. We're looking for the actual y value. So this y value here. All right. So if we take a derivative of g prime, we got to take a derivative of the other side. So we're looking at f prime of x. I agree with Herbie that we're going to be plugging in that -3 from the question. Now we're looking at f prime, looking at a graph of f. So what does a derivative mean on a graph? Slope. So looking at that guy, that's going to be the one, because now we're talking about the up 2 over 2 or the up 1 over 1. We could do 2 over 2, 1 over 1, whatever you want to answer as. This is a free response, so you can answer either one. The bathroom has been wild today. All right, so this is a very set of popular questions. You can notice that we can include a lot of different things in calculus in one question. So not only am I talking about like, oh, there's area accumulation question, but I'm able to connect derivatives and slope. Very, very popular, very cool. Hint, hint, nudge, nudge. You will see this again. On like a note check and a test. Yeah, there's one literally right here. Look at this fun graph. It's the notes check.
That would make more sense.
Yeah, you didn't want to take a test today?
No, I thought you wanted to have it.
All right, now I'm going to tell you a story. We have one more thing to learn today. And it's called average value. So I'm going to tell you a story. Imagine you have an aquarium full of fish. Normally that aquarium, when it's standing still, has like a constant height of water, yes? If you say walk up the stairs, hello, Connor, that water may begin to jiggle around. So what we're going to find, good question. Are you sure? Sure. We're on a good break. Take 2 minutes, say hello to your neighbor. Yay!
I don't know.
No.
You can't do it. You can't.
I wouldn't do that because this is good. You're probably going to want this to make the one.
Yeah, see, you can't do it.
I would think that substituting something from 3 gallon probably. It might have a serial number. Oh.
I think.
No, the base of that. So you get the interval for the. So that's true. It looks almost like the Q one, but there's a little bit of a correction. Yeah, you're gonna need to plug in something for one. Yep. All right, you have your aquarium. Yes.
I'm actually walking.
All right, we walked up the stairs. Our aquarium is all jumbled around, as is my screen. So what? No. You know what makes me mad? They've turned off my ability to turn off to turn on rotation lock. I'm not allowed. Yeah.
Why?
I don't know. Why can't I be trusted to not?
You're doing malicious things with rotation lock.
They gave us new computers and now I can't lock the rotation.
They know you're trying to like lock it.
I'm not. I can be trusted with my
You
computer.
should write an email to super.
I told the person who gave me this computer and they said, well, I don't know why. And I was like, yeah, they're very helpful all the time. They actually are very helpful. It's just not they just give the hardware. All right, so what we're going to try to find is something called average value. So imagine you have this aquarium with all the jumbly water. That average value is if everything leveled back out. So if I made that water, kind of staring at it from the side, a rectangle again, that's what I want my average value to be. Now, we don't use the word average very much in calculus. And we especially don't use it when we mean like take all of them added up and divide by how many are there. This is probably as close as you can get to that. But let me see if I have this graph. Desmos, log me in, bud. Did it? Oh, here we go. Average value. That's a slope field. So what I can do, let's go to our first question on here. What are we going to do first? 3x squared minus 2x. 3x squared minus 2x. Let me get. All right, so in this picture, let me give a better view of it. Let's go from like 0. No, we'll go from like -2 to 5, and this guy's pretty tall, so let's go from like -5 to 400. That's a little too much. Let's do like 100. There we go. And I'm going to bring this guy out a little bit more. All right. So you're noticing here that I have kind of a green area and a purple area. What? A gray area. Oh, like where they both are. So I want you to imagine they're kind of two different areas. So much happening. Would you agree with me that it looks like the green and the purple are about the same area?
Hello?
Why not?
Wait, like, are you including
Well,
like
there's also a
because
little
of,
green under.
There is a little
looks
green
like-
under.
Oh.
All right.
Then, yeah.
All right. I'm going to tell you those are exactly the same area. So this green area is represented by the integral of our function because it's curvy. I have to integrate it to find the area. This guy is our base times height. So those are exactly the same area. So the idea of average value is I want to find the height of this perfect rectangle. So if I laid it out and I made it into a rectangle instead of this curvy thing, on average, how high would that rectangle be? You can use this in a lot of different contexts, and we'll talk about it a little bit. It's going to end up kind of being like a formula that we memorize, but it comes from actually the mean value theorem. Remember when we drew those pictures with derivatives? It actually comes from a mean value theorem for integrals. So I'm going to compare that a little bit, and then we're going to do 2 questions and kind of be done for today. All right. So mean value theorem actually had to do with derivatives. So I'm going to write down this statement. Hopefully it looks a little bit familiar to you. Is this looking familiar to anyone? A little bit, a little bit.
Yeah.
So we have our instantaneous rate of change. Is equal to our average rate of change. So for this, we talked about like if on average I go to work and I drive to work and on average I travel at like 45 miles an hour. At some point I had to be going exactly 45 miles an hour because the way I drive is continuous. I don't time travel and differentiable. I don't automatically just like switch speeds. I have to go through all of them. So this actually looks very similar to this guy if I move him around a little bit. So this is the mean value theorem, or not mean value theorem for integrals. That's going to be in a second. This guy that we're working with says, hey, take this area, and then here's this perfect height of this rectangle that I want times the base of that rectangle. So notice from A to B that's our interval. So this is kind of the length of that purple rectangle that we saw. And this is the height. That's going to be what we're calling our average value. What we could do in this case to make these look a little bit more similar, if we integrated, took the antiderivative of little f and plugged in our bounds, we could do like a big F of B minus big F of A, where big F is the antiderivative of little f. And we could divide by that B minus A. Notice that these are the same formula, just moved around a little bit, and using some calculus definitely moved around a little bit. So just a comparison, the mean value theorem for integrals, mean value theorem for regular stuff, they are the same formula, they just look a little bit different. So what are we going to actually use from this? We're going to use a formula for this average value. This guy right here that represents the height of that perfect rectangle if our kind of function leveled out and just gave us a base times height. So that height is going to be our f of c here. And we're going to take our integral and we're going to divide it by the length of our interval. So the integral is going to find us our area. And then we're going to divide by the length of our interval to find on average how high it is. Now, most textbooks will have a 1 over b minus a out front to represent that division. If you're more comfortable, you can also write it as an actual division problem. So I think this is the closest we kind of get in calculus to having average mean, add them all up and divide by how many are there. Integrals often make me think of Riemann sums. So think of this as like adding up all of your infinitely many rectangles and then dividing by the length of that interval. So dividing by how many rectangles are there. So you get that perfect average height. All right, so how does this actually work? We got a function, we got an interval, and they say find the average value. So not a very creative question in this case. What we're going to do is we're going to set up 1 over b minus a. What do you think b minus a is going to look like for this question? 4 minus 1. So we're looking at our interval. All right, my integral is now going from 1 to 4 of what function? Yeah, f of x, so 3x squared minus 2x dx. So this is not very like enthralling. It's a kind of boring problem. So the dx, there's a couple of ways to think about it. It's mostly for us, it's going to act as like an end parenthesis to our integral. So it acts really notationally for us. Connecting back to Riemann sums, that was kind of the width of our rectangle along the x-axis. Now that we're integrating, we have infinitely many rectangles, so that dx is like super small. So conceptually, it represents something. Really, for our sake, it's going to represent like an end parenthesis to our integral. All right, I'm going to have 1/3 out front, and let's do this integral. What's the antiderivative of 3x squared? All right, add 1 to new power. Divide by new power. 3 divided by 3 is 1. How about 2x? Add 1 to new power, divide by new power. Done. What's the notation to say, hey, I took the antiderivative, but hey, I didn't plug in my bounds yet? No, we do not, because we have bounds. We're going to do that vertical line, and we're going to throw the bounds on it. Herbie's right. We are going to drop the plus c because we have bounds. If we didn't, we just have plus c in the front, plus c in the back. We'd subtract them. They'd cancel. All right. So 1/3. Which bound goes in first? 4. So we have 4 cubed minus 4 squared. Then 1 cubed minus 1 squared. Ooh, that's convenient. What is 1 cubed minus 1 squared? Thrilling. All right, anyone happen to know what 4 cubed is? 64 minus, I know that's 16. What is 64 minus 16? Is it 48? I want it to be 48 because that's divisible by 3. $40. 16. So let's connect back to this graph because this is the one I have graphed. What does that mean? It means on average, if I look at this function 3x squared minus 2x on the interval 1 to 4, on average, it is about 16 tall. So let's get this back to 4 and get this to 1. We zoom in a little bit. It looks like it would be exactly 16. Also note that the green area, the purple area, what I'm claiming is those are exactly the same area. That's the 48 that we got. Notice here, I'm using our average value. That's that 1 over b minus a to find that 16. Yep. So that would be how you could find the area of the rectangle. So our job is really to find the 16. So to find the area of the rectangle, we're finding the area of the equivalent thing, that integral, and dividing by the length.
Ask us to find the area of the triangle, more so just gonna ask to find the height of the rectangle.
Kind of, yeah. So the area of the kind of triangle-y piece, that's our integral. So we might be asked to find that, probably not in the context of average value, but this average value gives us that. Yeah.
So is it just the function that we're mentioning? Like, what does that purple box have to do with it?
So the purple box kind of gives us the idea of what this average value is. I can turn that off real quick. So what the purple box is doing is it's kind of showing you the equivalent area. The question that we're asking is, on average, how tall is this function? So an easy way to visualize that is to imagine it flattened out and has just that one height. So that's what that visual is doing. But
average between.
Yes. So because this is curvy, we can't just take like the middle height of this. So we're using calculus to kind of find the area and then dividing by the length of the interval to find that.
So the right bound out, the box would get.
Exactly. So I can actually do that if you would like to see. So you'll notice as it goes in, it gets smaller. As it goes out, it's getting larger because we have more area that's flattening out, and it's getting taller faster. So we have a larger average height. So kind of since what? It does get very small. All right. So I don't know about you, but this question was not the most enthralling to do. It's not the kind of most fun because I didn't have to interpret everything. It just said find the average value. So how else could I ask about this? Average value can give you the average of a function that you already have. So we can use this a lot in the context of position, velocity, acceleration. I find this to be one of the more interesting uses. So let's say we got a dog. This is not my dog. This is a random dog. But let's say we're given that velocity function. Here, we're finding average velocity. Our interval is going to be 1 to 3. And here, we can't use an average rate of change, because if I used an average rate of change, like a f of b minus f of a over b minus a, I'd be getting average acceleration. I'd be finding the rate of change of that. So I want to find the average value of a function I already have. That is why I'm about to use this kind of formula that we have here. So I'm going to do 1 over 3 minus 1, like Matt said. Interval from 1 to 3 of this function right here. Essentially, if you're thinking physics, what this is doing, the integral is going to take you from velocity back up to position. And then since you're dividing by the interval of time, that's going to bring you back down to velocity. Yes. Technically, you could swap the bottom if you also swap the bounds, but since we usually do bounds from lowest to highest, we would do highest to lowest in our subscription. So this is what's doing our average value here. So this is dividing by the length of our interval. So that's what's taking me back to the velocity function. All right, let's see if we can integrate one more time. I'm gonna leave this 1/2 out in front. What is the integral of negative t squared? All right, negative 1/3 t cubed. What about 2? So raise the power by 1 and then divide by the new power. Antiderivative, yep. What about the, when do we plug in the top bound? After we do the antiderivative. So what is the integral of 2? 2 what? 2t. All right. Notation that says, hey, we took the antiderivative, but we didn't plug in our top bound. The line, and the bounds go on the line. What bound goes in first? 3. So I've got negative 27 over 3 plus 2 times 3 minus 1/2 negative 1/3 times 1. What? Yes, always subtract. And plus 2. All right, since I have a feeling we're done, I will simplify for us just so we have an idea of what that number would be. It would be negative 7/3. What does that mean in general if we get an average velocity of negative 7/3?
There's always a way
All right, yeah, whatever this dog is doing, it's running backwards most of the time. Did it have to be running backwards the whole time? Yeah, on average, it's running backwards. Yeah, good. Nice. Running backwards more than it was running forwards. All right, cool. So as we move to the end of this unit, so kind of looking at this guy, we kind of finished FTC and average value. Applications of integration, there's going to be two big ones that we're going to work with next time. They are both big deals on the free response section of the AP test. So we're going to be doing one of my favorite free responses, which is called a rate in, rate out question. So one of the ones in recent years, there was like a table of bananas and people were putting bananas on, taking bananas off. Very cool question. We'll walk through that one. And then we'll talk about position velocity acceleration. What? I don't like bananas very much, unless they are part of a bread. My husband eats a lot of bananas. I prefer more expensive fruits. Not because they're expensive, but because I like them. I don't know if I've ever had dragon fruit. Which one is that one? What does it look like?
The outside is like it's like pink.
And the inside is the white with the black dots? That was creepy.
You don't like it?
No, I just find the coloring weird. Naturally occurring white fruits are strange. All right. So you got 3 questions on a notes check. You guys can work together. There's one version. I will tell you, first question looks like one of these from the 6.4. Second question looks like one of these. Third question looks like that. It's almost like I tried to prepare you. I want this before you leave. Ask me questions. Ask your neighbor questions. Where are we going? How are you just done? You can just throw it anywhere. Preferably not in the trash. Thank you.
That would be kind of awesome.
I know, right?
For my whole research would be nothing.
The end of the 6.4 notes that we finished at the beginning of today, where we used the fundamental theorem of calculus. So if you're doing number 1, I would look at this back page of the 6.4 notes that we were doing. I'm just going to let you guys roll. Yeah, I'm going to figure out how to rotation lock